Hello and welcome back to another episode of Through the Looking Glass, featuring myself, James Lassoff, and my co-host, Richard, aka the Mad Hatter. In this series, we dive deep into all things AI, hence me being joined by the expert AI nutcase himself. Our first question of the day, Richard, is how is data processed differently within a CPU rather than a GPU? And where do they both have their place?
Cool. Yeah, so that's obviously it's a very important thing to understand, particularly in the world of AI. We want to understand sort of why all of a sudden GPU is the thing. Why is it the big in vogue technology? So it's the fundamental difference is how they approach the maths that they need to do. Because at the end of the day, CPUs and GPUs are effectively calculators, very, very, very fast calculators, but calculators. Now, I like to define the difference in a way that your CPU is like a doctoral mathematician. He is phenomenal. He can do all the maths and all the weird, complex, wonderful maths. Whereas your GPU is like a bunch of grade school children who can do relatively simple maths, but there's many of them. And the logic there is that certain kinds of workloads make more sense. Let's take a step back and say, if you have an objective and you have 5,000 simple mathematical requirements, it's going to be easier to give it, or you're going to get it done faster if you give it to the grade schoolers than if you give it to the doctoral mathematician, because he still has to do those sums one at a time. Whereas you can give each child one sum and they can do that. Uncomplicated maths, many in parallel. Whereas on the other side, the CPU, when you need to do complex things, you need your doctoral mathematician to do it.
So that's a great way of looking at it. But it does raise one question, maybe a concern or red flag that people might come to their minds. And that is, we often throw very complex problems at these models at these GPUs. And if we've got grade school level thinkers in this metaphor, solving these complex problems, how can we ensure they are correct and accurate? How can we validate them? And could you potentially use the CPU as a sort of moderator to confirm the GPU's calculations?
So in theory, you could, absolutely. I use the grade school just as a sort of a metaphor, but obviously it's quite a lot more complex than maths. The doctoral person can do extremely complex maths, brilliant maths. Whereas let's maybe say a bunch of high school students, hardworking high school students, are the GPU type workloads. When we write the code, we're writing code that only takes advantage of this kind of maths. So there's a very specific kind of maths. And so when we do that, we say, right, your execution needs to go to the high schoolers because they're all capable of doing this for me. Whereas the CPU, okay, my GPU can't do this kind of maths. I need to feed it to my CPU. So we give them a different kind of workload. So the CPU can, in theory, be used as a moderator, but the CPU is going to do the same maths. It's just going to redo the same maths. And the CPU, and again, like that metaphor in the beginning, your CPU is going to only be able to do it like a single doctoral mathematician. He'll only be able to do it one sum at a time. So he might be able to do those sums a little bit faster than the high school kids, but he still can only do one at a time. So if there's 1,000 sums the high school kids need to do, he needs to do 1,000 sums, one after the other. Okay. And that's where it's in a way kind of the art/science of figuring out where your workloads live best. That's where you do that.
And on that, how does the compute or the software you're running, the LLM, how is it decided which workload fits best as a CPU workload or GPU workload to avoid the CPU doing those 1,000 basic sums?
So that's typically actually the responsibility of the person who's building, let's say the LLM, for example. Their responsibility is to make sure that the way that they architect their code conforms to what is available to them within the GPU. And it's only because the GPU is what enables that kind of sum, is what enables the LLM's thinking. The thinking that the LLM does is actually a fundamental component or fundamental almost architectural design that is provided by how a GPU works. So it's kind of like this weird chicken and egg in an odd sort of way, where the one informs the others the way you use it and deliver it. So if you're building an LLM, you want to take advantage of parallel maths. And LLMs themselves work effectively. It's LLMs at their fundamental level. I think we've discussed it previously, is a vector database. And vectors are effectively just maths. Right? It's a whole bunch of sums, uncomplicated sums, but it's millions and billions and billions of them. Parallel information, but uncomplex in each iteration. It's not a complex thing, a vector, but in its sort of in the package that it comes into, you need to be able to do all of it at the same time. That's why GPU makes more sense for that kind of workload.
Thank you, Richard. And that's a great little Easter egg he's thrown in there that we will surely be diving into soon. We've got some very exciting news on the horizon with regards to vector databases.